Good day, everyone. I'll be discussing our objective and scope of our study. The primary goal is to analyze the mechanical performance of a shallow rigid strip footing on a stiff clay. Additionally, we are aimed to compare the result obtained from the finite element method with the empirical formula to validate our finding. Yeah. So the scope for this analysis is like we'll be utilizing Strand 7 software. Our investigate will include an assessment of soil stiffness sensitivity and in-depth analysis of stress, strain, and force displacement relationship within the soil foundation system. As you can see on your screen, we have taken this type of footing and where the breadth is 0.8 meter and the depth is 0.2 meter. And, and the general specifications for our sample is given as the Young's modulus and undrained shear strain CU is 85 kilopascal and Young's modulus for soil is 21,000 kilopascal. And we have taken the density of our stiff clay is 1800 kg per meter cube. Lastly, the Poisson ratio is set at 0.49. This comprehensive overview sets the stage for our detailed analysis of the shallow rigid strip footing on stiff clay. Yeah. So for this presentation, our constitutive models uh, in our finite element method analysis is crucial to understand the soil in complex, nonlinear, and path-dependent material. This complexity means we need to consider both the strength and deformation characteristic of the soil. You can see the Moore column model equation is given by tau is equal to C plus sigma 10 phi. The FEM mathematical analysis is dealing with 2D strain problem. This process involves discretization where the domain is divided into finite element connected at nodes within these element displacement and approximated using space function. The equilibrium equations are derived from the principle of virtue work and weighted residues. The soil behavior, we use various material models such as elastic, elastoplastic, and viscoelastic models. Finally, our analysis considers specific boundary conditions, including fixed support and applied loads. And now my friend Akash Bhatia will be presenting further slides.
Hi, I'm Akash Bhatia and I'm presenting you the FEM modeling in which Strand 7 is used, which is a powerful software capable of conducting various type of analysis, including linear, static, buckling, and non-linear static analysis. And in our case, we are using non-linear static analysis in formulating the FEM analysis model. The constituent elements were determined using Strand 7 software, and the model consists of several quadrilateral elements with the utilization of quad 8 to ensure the higher accuracy and prevent the formation of elongated elements. Next slide, please. Coming on to the meshing, and in this, the meshing was adjusted based on stress consideration, employing finer meshes near the foundation soil interaction to derive more precise stress calculation. Additionally, finer mesh on the side facilitates the accurate calculation of axial resistance values. The mesh gradually transitions from finer to coarser from the bottom of the footing towards the end of the soil. As you can see in the figure mesh A and mesh B. Coming on to the dimensions of the boundary, as you can see in the last thing, and coming on to the next slide, can you please move to the next slide? In this, the subsequent steps were involved in specifying the boundary conditions. Fixed conditions were applied to the base and sides of the specified boundary while permitting vertical displacement at the symmetrical axis and the sides of the boundary. Specifically, U is equal to 0 and V is equal to 0 for the base boundary, and U is free and V equals to minus 0.08 meter for the base of the footing. For the rest, you can see the table below. Coming on to the next slide, where the load is being applied on it. So the displacement is used in which the displacement should be applied to the soil part interacting with the footing. In our model, the displacement is applied to the soil at the base of the footing. The displacement is usually divided into increments, and the division of increments of our model are taken in specified percentage. For example, 0.1%, 0.5, and goes up to 100%. And the values of increment are follows as well, like 0.001, 0.005, moving on to 1. And the application of load, which acts in the vertical direction in the footing, is done by using the attribute option in the strand 7 toggle bar. And then a non-linear static analysis is being done. For the next part, Lan will gonna continue.
Thank you. Next part is the FEM results analysis. For the first part, we have the mesh A and mesh B. Mesh B has the transient areas of the elements, so it's usually better. So if we can see from the next slides, please. Yeah, this measure is coming with transient areas. Usually, this will be better simulating the actual soil behavior. Next slide, please. Too much. Yes. The FEM results calculation. For comparison of the FEM results with the conventional results, we used the AW equal to different values for the computation of different CU values, where the AW is the amount of the cement added. The CU value for the case 1 is 85 kilopascal, and the P shaft is gathered from the FEM results, which is located at the site of the vertical of the footing vertical sides, and the P base is calculated and gathered from the footing down below, and the nodal reaction of Fy is collected. So in that way, we will be able to gather the P base and the P shaft value. Next, please. So as we talked in the previous slides, the P base and the P shaft is gathered together, and adding them all up, we need to multiply them by 2 to simulate the actual place that we are only taking only halfway of the sample. So the total PU is calculated as the 533 kilopascal in different displacements, and the bearing capacity and the displacement is showing on this graph. And this part is a result of the comparison of the PU. From the conventional from the conventional methods, we can calculate the PU is equal to F base plus the F shaft. The area of the base multiplied by NC value and CU value plus the area of the shaft multiplied by CU. In this way, the conventional method will calculate in the PU as 401 kilopascal, which is slightly less than the 532 kilopascal from the FEM methods. Next, please. The NC value validation in this part is calculated in the following way. The P base is equal to area of the base multiplied by CU and multiplied by NC. So the first 3 numbers are determinable. So the NC can be determined by simple calculation. The NC is equal to 60.02 with the FEM methods. As for the traditional method, the scheme-term graph is used, and the NC can be retrieved from this graph as 5.65. As we can see, the FEM and conventional methods, their differences are very similar, are very small, so we assume these results are satisfactory. Next. This part has some
Now let's discuss some common FEM errors and their solutions. The error 1 is the mesh density. The inaccurate stress and displacement result can affect the result of our FEM model. For example, sparse mesh leads to errors in displacement prediction by up to 20%. The solution is the increase in the stress and the density in critical regions or areas. The second error is the boundary conditions, the distortions impact the distortion stress distribution. For example, the fixed supports cause the unrealistic stress concentration. A solution is to verify and validate the boundary condition very carefully. The third error is the materials models is the missing is maybe cannot represent of our soil behaviors. For example, using a linear elastic model for plastic soil behaviors result in 15% of deviation in stress prediction. The solution is the collaborates the materials models with the experimental data. The second is about the mesh density for shallow strip foundations. We have two types of mesh. The mesh A is a fine mesh at the foundation base. The problem is already fine mesh increasing the computation times without significant accuracy improvement. Our solution is to use the balanced mesh density finer near the foundation base and keep it far away from them. And the impact is the accurate the stress distribution, but computationally expensive. The mesh B is we use the applying the transition elements. This is the problem is sometimes it will be getting the improper transition elements to cause stress concentration or artificial stiffness. The solution is to ensure the smooth transition in element size to avoid the abrupt change in mesh density. Impact is the effective, but it requires careful design to avoid the numerical issues. From our practical, we get some tips for the mesh design. First is gradual mesh transition. The second is the critical regions that we need to focus on some areas. The third is the mesh verification, because it conduct the study to ensure the accuracy. The part 6 is the conclusion. We get in the conclusion for the FEM analysis. We found that is a powerful tool for geotechnical engineering. The second is the accurate response representation of the soil property behavior is critical. The third is understanding the result of gap between the FEM method and the conventional method. The fourth is the nonlinear FEM analysis for the realistic